And with that, I want to introduce our speaker for today. Professor Wynand Steyn is head of department and professor in the Department of Civil Engineering at the University of Pretoria in Gauteng, South Africa. He's a registered civil engineer with a research interest in pavement vehicle interaction, accelerated pavement testing, pavement engineering, pavement materials, Civiltronics, and instrumentation. He's authored a number of journals, book chapters. He's an editor. He's a fellow South African, I'm condensing here a little bit, Wynand, Academy of Engineering, and also an adjunct professor at Chang'an University in Xi'an, China, and Shandong Jiangsu University in Jinan, China. And Wynand has been working with the Pavement Research Center at UC Davis since 1995, before we even came to Davis. So with that, welcome, Wynand. You might, if you want questions during or hotel after, you might.
If you've got a question, if something is not clear or so, and just put up your hand and stop me, and then afterwards we can do more questions, but please. John, thank you very much, and Marie, thank you very much. It's really a privilege to be here, and I hope you enjoy the presentation. I tried to not show you 50 equations because it becomes a bit boring. But I hope that what you gain from the presentation is a better understanding and appreciation of why you are studying what you are doing. And that there is a bit of a bigger picture than equations and materials and stresses and strains and stuff. So what I'm talking about is pavements, freight vehicles, we all need and affect each other. And a bit of background about the why, how it's working and so on. Is if you look at the three parts there, pavements, freight vehicles, what are we doing? Most of you guys are involved in either pavement engineering, road engineering, transportation, so stuff that moves. And what are we doing? We are designing pavements and transportation systems. We construct them, we maintain and manage them. It's part of our job. Why do we do that? Because we've got road users. I will repeat this a few times during the lecture because I think it's something that we often tend to forget. You get so bogged down by the material properties or the details of the transportation model that you are working with that you forget the fact that what you are doing is something for the general good of the population that needs to move. So that's what I would like to focus on a bit in terms of the discussions and so on. So why are we doing this? How are we going to go through this? I'll give you some background on a bit of numbers and a bit of why it's more detailed and why we want to move and so on. And then very specifically, as John has indicated, I've worked in vehicle pavement interaction for many years. And a bit of background on that. Why is it important? Why does it affect your lives? And then use some of the agricultural transportation examples of work that we've done in California and South Africa as a way to explain some of these bigger issues and how your little bit of work that's very important can fit into a bigger picture and can affect the general population out there in their day-to-day lives. And then lastly, a few things that sort of ties together some of the instrumentation and some of the more future thinking about what we are doing. Okay, so just to give you some perspective, and I decided to use South Africa for this because obviously I know the picture a bit better and so on, but as a general idea. South Africa is on the southern point of Africa. A good way of naming a country. It's on the southern part. And it's very much similar to you guys. North America, northern part of America. So it makes life much easier in terms of naming it. We've got a road network of just about 750,000 kilometers of roads. So that makes us the 11th longest road network in the world and the 18th longest paved road network in the world. But what's quite important is that about 80% of that road network is gravel pavements. So although we've got this huge network, if you look at it over there, that's the center of the economic activities of the country. Johannesburg, Pretoria, my university is just over there. The blue roads that you see is our national road network. our interstate, if you want to say it like that, connecting the country together up with the northern countries in Africa. But then you've got the red lines there, which is the more provincial type of roads. You've got the smaller ones. And in the end, it's important to appreciate again that although most of your work that you are doing, and that you will see if you start to talk to people about pavement engineering, about transportation models and so on, most of our work focuses on interstates, highways, major traffic type of roads. Because yes, obviously that's normally the more economically important ones. That's the one that if something goes wrong, you've got a bigger problem and so on. But all these smaller ones that you see over there is as important for somebody that lives there as the big highway. And you have to understand that, you have to understand the context, and you have to understand how much importance you need to give those roads and access in those areas, and how to balance your limited budget. And that's another part that I will also get back to a few times during the presentation, especially once we get to the agricultural part of it. It's a good ideal to say that all roads should always be in a perfect condition. I mean, if you talk to non-engineers, that's sort of obvious. I mean, that's why complain about the state of the roads. There's some cracks on the roads, it's not good. There's a pothole on the road, it's not good. And don't hear me wrongly, it is not good if you've got a pothole on the road. But if it's the one road that goes to your house and it's only you that uses that road, it's not the end of the world if there's a small pothole on that road, because you've got a limited budget. And you always will have a limited budget. Whether you are living in South Africa, Nigeria, America, China, you will never have enough money to do everything. So you have to optimize, you have to decide what's the most important parts. How do I get the best solution to the problem that I'm working with? So that gives you a bit of an idea. We've got 59 million people in the country traveling on those roads. And just as an interesting fact that's very important for your if you're looking at rather writing an assignment, just over there where you see that there's not too many roads, that's where the next land speed record will be attempted next year. The guys from the UK, the Bloodhound project, that area over there is very dry and very flat. So they've done their last test about 2 months ago there. Went up to 1,000 kilometers an hour with their rocket-powered vehicle. So that would be a nice idea for your assignment if you miss the questions. Go and check for Bloodhound. So sometimes you don't want people around, you don't want roads around. That's a much easier way to run what you're busy with. Yes?
Just as a note, I think California is also 40% gravel roads, and I think nationally it's about 50%.
Okay. Gives you a bit of perspective, South Africa, and we've got the biggest percentage paved road network in Africa, is 20%. So if you look at California, then you guys are about 60% paved, and the country, the US, about 50%. And keep in mind that also depends on the economy, how much money have you got, and why do you have the roads, and what do you use them for, and what does the environment look like. If you look at our country over there, we've got some snow now and then over there, the mountains over there, and in the mountains over there. Further on, we don't have snow on the roads. So anyway, so it changes depending on the environment of what do you need to do on your roads. Keep that in mind. Okay, so brings us again to the why. Why is all of this important? Why do people need to travel? They need to travel for social reasons. They go and visit people. They need to travel for economical reasons. You need to get to your job. They need to travel to either collect food or to distribute food. And that would be important for the second part of what we are talking about. And as an example about that, if you're talking about transportation and logistics and movements, it's never a simple solution, because if you look at the pictures, that guy is transporting tomatoes, those guys are transporting tomatoes, that guy is transporting tomatoes. So all three of them transporting a vegetable from one point to another one. But depending on the need and the requirement and the market and everything, there's a total difference in terms of the transportation needs and the road needs and the pavement needs between those three aspects that you look at. Other reasons why we need to travel: education, Safety and security, health, you need to be able to get to clinics, hospitals, and so on. So a lot of reasons why people need to move stuff. And whether the stuff is other people, themselves, goods, whatever the case may be, you want to move that in a safe and economical system. So you want to make best use of your limited budget, and you want to be able to have a bit of a guarantee that if you travel from here to San Francisco to, for whatever reason, you've got a pretty good probability that you will arrive there within a certain time. That's something that you expect. So if you look at that, you guys in this room need to remember, you've got a job or a future because people need to travel. Because if you sit back and think about it, people don't need to travel at all. Who of you will still have a job? What are you going to do? Because what you focus on is how to make people travel better over the long term. Keep that at the back of your mind. Okay, so with that in mind, let's have a bit of a discussion about vehicle-pavement interaction. What are we talking about in terms of vehicle-pavement interaction? Why is it important? How does it affect your life? One easy way to summarize that is this drawing that was actually developed around about 2010-11 in a project that we've done together with Caltrans, and you see it was Davis already at that stage. Yeah. And what he tries to tell you is you've got a vehicle traveling on a road, and you don't have to be a pavement engineer to understand this part. All of you have driven on a road, or you were in a vehicle driving on a road, and sometimes you drive on a road and it's nice and smooth. And sometimes you drive on a road and it's a bit bumpy. And as it gets more bumpy, typically you have to drive slower because it's not safe anymore. And that bumpiness or evenness of your road is what we call the riding quality of the road. There's various other terminology that you may see. Let's keep to riding quality for now. And riding quality is essentially measured or defined as the amount of vertical unevenness over a certain length. So if you take a sort of desk running down here, if I have to describe the riding quality, you will measure at certain points how level all of these desks are, and you will see that there's a bit of a change in the smoothness, and you will get a value that will tell you it is 10 millimeters over 20 meters of roughness. And obviously the higher this number is, the more unevenness you've got on that road, and the worse the riding quality and the driving conditions on that road is. Now the reason why this is important is as a vehicle drives on a road where the riding quality deteriorates, a road that's more bumpy, a few things happen. Firstly, you increase the damage to the vehicle. So your vehicle may not fall apart on day one if you drive on an uneven road. But over time, because you've got more vibration in the vehicle, you start to get damage on this vehicle. And there's very good studies that shows this. That increased damage to the vehicle increases your maintenance cost on your vehicle. That increased maintenance cost increase your logistics cost in terms of transporting goods. And all of that increases the cost of your transported freight. So if you want to buy a beer that comes from somewhere else, if the road is rough, then the guy that transported it to you will have to charge more to deliver the beer to the shop where you go and buy it. And what does the shop do? They ask you more for the beer, because who else is going to pay for that? So the fact that the road is not in good condition, it's got an additional cost on the vehicle that you have to pay for. Apart from that, there's also increased what we call road loads. So as your vehicle drives on this road that's uneven and it bumps up and down more, obviously every time that it bumps up, it's not too bad because there's less load on the road. But as most of you would know from basic physics, it has to come down again. And wherever it comes down, it starts to damage the road more. That causes increased road damage and road maintenance costs. And that also have got an increased environmental cost, because now you have to come and fix the road earlier than what you planned. So you need asphalt earlier, you may need other materials earlier. So there's an environmental cost also to this unevenness or bad condition of the road. Then that unevenness on the road also increases your fuel consumption. Again, very good models in terms of this. The worse the quality of the road, the more fuel you use to travel the same distance with the same mass. Again, an obvious increase in environmental cost, but also increased vehicle operating cost. So if the guy has to drive on a bad road to deliver your bread or your beer or whatever, you are going to pay more. And then the last one, as you drive on that bad road, is that you start to get more damage to your transported goods. Obviously, everything bumps up and down more. Whatever you load it onto that vehicle will start to get damaged. And there's different ways of solving this problem. And this is normally where people come in and they say, oh, but don't worry too much about the road, because we can improve the vehicle properties. We can have a better suspension on the vehicle. We can have a vehicle with better tires. The problem with that is that I've got 1 mile of bad road. So each and every vehicle that travels on that road needs to have the better, more expensive suspension to prevent that damage. Or they come and they say, well, it's also easy, we can just improve the packaging. And it's possible, but if you now transport tomatoes on this truck, and there's a bad road, it means you have to improve the packaging on each and every tomato. Whereby if you change the condition of the road, get the road to a better condition, then you don't have to spend that cost. Because again, damage to transported cargo goes to increased cost of your transported freight. So whatever you do, if the condition of your road starts to deteriorate, your vehicle-pavement interaction will cause increased costs in various ways in terms of this bigger model. So riding quality of a road is quite important for us. It affects everything in terms of that road. The operating cost, the vehicle cost, as well as the maintenance and rehabilitation cost. Another reason why riding quality is quite important is this example of what do we know if we know the riding quality of the road. A road can deteriorate because of many problems or issues. To make it simple, you can have permanent deformation, which is rutting, or you can have cracking on that road. Whatever goes wrong with the road ultimately is visible through worsening of the riding quality. So that's why we see measuring the riding quality similar to you going to the doctor because you don't feel well. And from experience, all of you will know if you go to the doctor and you say, listen, I don't feel well, apart from the fact that you are bleeding profusely because you cut off your hand or something obvious like that, the doctor will listen to your story and say, thank you very much, come and sit down. I want to take your blood pressure. I want to measure your temperature. And those two indicators is not really going to tell the doctor what is wrong with you. But if the blood pressure or your temperature is outside of normal limits, it will start to tell the doctor, well, maybe you are really not feeling well. And maybe they need to look a bit further into this. If you come in and you say, listen, I really don't feel well, and your blood pressure is normal and your fever is good, they will probably ask you, so what exam are you writing tomorrow? Because it's sort of, listen, everything is within spec over here. So it's an indicator of the health of the body. And in the same way, riding quality is an indicator of the health of your road. Over time, again, many studies have been done on this where you can see that as you use a road more and more, the riding quality typically deteriorates. So it's a standard feature of a road. It's not a road that's badly constructed. It's a standard feature. Over time, it will deteriorate. And you will have to, with use, get to a point where you do some maintenance and some rehabilitation to that road. Okay, so in terms of what happens to all of this cost, I've got these vehicles with freight traveling on the road. I've got my riding quality that changes. If you look at what we call the logistics costs of transporting stuff, and this is an example of our South African ones, you will see you've got transport, which is this major part here at the bottom that runs at about 50 to 60% of the total cost. Then you've got other stuff also, inventory carrying cost, warehousing cost, and things like that. But you can see that in terms of getting stuff from point A to point B, although there's a lot of other costs, your transportation cost is a major part of that. So being a 60% part of your logistics costs means that it's important, but it also means that if I can manage this part better, I can maybe cut down on that total cost significantly. whereby if I ignore this major part of my bigger costs, it's very difficult to get away from that and to save in terms of transportation cost and drop the cost of goods that you have to deliver. So let's now get to something that's a bit more close to an example of why these things are important and how you can see them in your day-to-day life as transportation engineers, pavement engineers, and road users and people using goods that's transported on roads. So in terms of the projects that led to a lot of what we are talking about here, as I said now, riding quality is indicative of road condition, and it affects your operating cost, affects your transport cost, damage cost, and so on. So in about 2010, we had a discussion during some of our meetings over here with Prof. Carl Management still at that stage at Berkeley, in terms of, we know this is important, but how do we actually characterize this cost? How do we quantify it? How do we get to people that's in places where they decide on a roads maintenance budget and convince them that a road with a bad riding quality really needs attention? Because the problem with riding quality on the one hand is that the road is not falling apart. You can still drive on the road. And you don't really see that it's bad. You may need to drive a bit slower, but it's not the end of the world. So it's very difficult to convince the people with money to spend more on a road that's in a sort of not bad condition to improve that, because that will lower my logistics costs, and it will lower my operating costs, and it will lower my environmental costs. So at that stage, we started what I will call the Caltrans projects in 2012, some of the measurements in terms of transporting agricultural goods. And then once we started with that, some of my local guys in South Africa heard about it, and the biggest tomato producer and avocado producer there contacted us and said, listen, can you do something for us also? And it grew, and the latest study is one that started end of last year. And I will take you through these examples now and show you partly why vehicle pavement interaction is important, but also quite important how technology changes over time and allows you to do more and more things, get a better answer than what you have been able to do previously. That's also, I think, also quite important. You guys are studying now, you learn new techniques, you learn about sensors or stuff, and you think, wow, I get a degree, I know all of this stuff, I now know how to do my job. The bad news for you is in 5 years' time, there will be better technology, better methodologies, and most probably different questions to answer. And you will realize, oops, the stuff that I knew 5 years ago is not enough to answer questions in a good way anymore. So, let's start. First project that we've done was in 2012, started there. Up until that point, if you wanted to measure accelerations in a vehicle, accelerations in a vehicle, for the context of vehicle pavement interaction, is basically measuring how much the vehicle bumps up and down as you drive on a road. You had to install accelerometers on the vehicle with wires, with a big data acquisition system on a computer, and then you could collect a lot of data. Now, if you look at the truck like that the farmer uses to get the tomatoes from the farm to the packers and so on, you can think for yourself, if you have to get permission to install a lot of accelerometers at certain places with wires and everything, it's very difficult. So in our evaluations at that stage, we got hold of a little sensor, and I'll show you, it's a bit bigger later on, but you can see that there in the circles, it's about that big, it's a standalone accelerometer, and it provided us with the opportunity of instrumenting a vehicle at different points, also inside the tomatoes that's being transported, drive over a number of roads, and collect the riding quality as we drove. And also collect what happens to the cargo, the tomatoes in this case, as you drive on those different roads. So we could measure the actual riding quality of the road using different technology. We can measure how much the vehicle is reacting to these different roughnesses of road, and there you can see different roads. And we could measure what will happen, we think, with the tomatoes sitting over here in this vehicle as it bumps up and down. So taking all of that data, and this is one specific road section, we had the measurements and we said, okay, but now we can start to see how much of an effect it really has. So in terms of the road roughness measurements, I just get to the colors for now. You can see that there's a green section, and then there's a red section that's worse, and the yellow section that's sort of in between in terms of riding quality. So we've got a good section, a medium section, and a bad section. Same section of road. So you drive from here to there, and due to various reasons, you've got these different qualities. Now, if you convert that through various calibrated models, you can also transpose that to the tire wear on the different sections of road. And what's interesting over here, and I think that's also important for your understanding of different types of models, you will see that we've got three different levels of roughness on the road. But in terms of the tire wear, there's only a tire wear over there, and those two sections, although it's a medium and a bad section in roughness, they gave a similar output in terms of tire wear. So the fact that your riding quality has got sort of more subsections does not always mean that whatever you calculate based on this will also relate in the same way. So that for the tire wear model, it showed us that was not too bad, that was a bit worse. In terms of repair and maintenance on the vehicles itself, we again got different outputs in terms of tire loads and emissions and fuel consumption. We could also show the differences. So the benefit at that first point was that you could say, okay, if you transport tomatoes, this type of vehicle, on these roads at these speeds, you can see that in terms of fuel consumption and therefore operating costs, you will get different responses on different sections of this road. Which obviously will tell you that if the cost on that middle part, because that was the worst part with the worst riding quality, becomes too high because of bad riding quality, if you fix that road, if you improve the riding quality of that section, you should drop the cost on that section of road, you should drop the tire wear, you should drop the repair and maintenance cost. So ultimately you drop the logistics cost of transporting your tomatoes. So that was part of what we got out of the first part of the test. Now in terms of the sensors that we used for that, what you see on top is the accelerometer. It's about that big. Was really a major step forward at that stage because you could just bring them out, you fix them to the vehicle, fix them into the tomatoes wherever you want them, do all your data collection, get back to your lab, download the data, and you've got a full picture of what happens over there. So that was quite a step forward. At that same stage, sort of halfway through this project, we got hold of another type of sensor. That's those flexible plastic contact stress measurement mats. Now, the benefit of those things, you will sort of see the little black spots on it. On that surface area, and you get different sizes, you measure the contact stress between whatever you press on top of that mat. So if I've got a tomato there and a tomato over there, I can measure the contact stress between those two tomatoes. As I said, this became available halfway through the project. So at that stage, we had data on how much our tomatoes bumps up and down in the field. We could not install this in the truck at that stage. So we got to the laboratory. We used the accelerations that we measured in the field. We made up these boxes of tomatoes with the sensors on the inside, and we applied the same accelerations in the laboratory than what happened in the field. And we said, okay, now we can measure what are the contact stresses between the tomatoes. Now you stand back again a bit and say, well, why do we do this? We are pavement engineers. We are interested in building a better road. We are doing this because this tells us what's the effect of our road on the tomatoes that's being transported. So we put all of that together and we got contact stresses. Now, the next problem is, if I tell you that the contact stress on the flat side of a tomato, if it's green, is 28 kilopascals, then you say, wow, okay, that's good news. And so what? I mean, if I tell you it's 400 kilopascals or 2 kilopascals, you start to get the values, but you need a relationship of, so what? How much damage is this? So that's where we started to engage with the agricultural people and said, okay guys, how do we now determine where's the cutoff point? What is bad and what's not bad? Unfortunately, they've got various systems looking at this. And the basic crude one that we used, which was not that bad in the end, was to say, okay, let's apply these stresses to a set of tomatoes. And you'll see that there's green and ripe, and you'll see later on pink and red. We learned a lot about tomatoes in the whole process. And we did damage a lot of tomatoes in the process. We also ate a lot of tomatoes. But basically we said, okay, let's apply 28 kilopascals to a tomato and put it on the shelf and see what happens to this tomato. And we also do it with 13 kilopascals and so on. And essentially we want to see, when does it start to look bad? That was for us not too bad from an engineering viewpoint. And you'll see in a few slides why that was actually not a bad idea to do that. So what we got from this up until this point was to say, we can use the relationships that we've got now, which tells us on that type of road, this is how much tomatoes you're going to bump up and down. And these are the stresses that they are going to feel. That helped us as a road user viewpoint to say, if I've got alternative routes available to travel from point A to point B, and I've got the riding quality of road A and I've got the riding quality of road B, this knowledge can tell me which of those two roads will cause the least damage to the tomatoes that I am transporting. Because I want to get it to the end point without damage, obviously. And if the distances are not that much different that the travel cost becomes exorbitant, then I can make that selection and say, I don't want just the shortest or the fastest route. I want the route that will cause the least damage to my projects. That's from a road user viewpoint. But from a road owner viewpoint, Department of Transport, it also started to allow them to say, but we can now start to quantify, we are not really there as yet, of why do we need to improve the condition of this road? Because as I said earlier, you can have a road with, from an engineering viewpoint, a pretty bad riding quality, but it's still rideable. So it's not that the road falls apart. But this started to allow the Department of Transport to say, but guys, there's actually enough wrong with this road because the amount of damage that it caused to the tomatoes is so much that there's a real cost over here. So that was the initial output that we got from that part of the project. Then we got back to South Africa, and as I said, we spoke to various people, and the guys at ZZ2 is the big tomato guys. They said, listen guys, we want to do it for South African conditions also. The benefit at that stage, development of technology, is that these are those contact stress mats. We got it to such a point that you could actually put it together with an inverter and a computer and stuff inside a bin of tomatoes on top of the truck. So we started to do that. We also had it inside the boxes because some of the tomatoes are transported in bulk. Some of it is transported in boxes. So we installed them, measured these stresses. You get this type of data out of them over time. And we've done it with various types of vehicles. So we had tractors in the field. We had bigger trucks. We had the big ones that we use on the highway. And on a range of routes that included roads in the field, smaller provincial roads, as well as the highway, we collected a host of data in this way. Still measuring the riding quality, actual riding quality of the road, still measuring the accelerations on the vehicle, but now, while we drive, measuring the contact stresses between the tomatoes. And the reason why this was quite important was this then allowed us, one of my students, Linky Pretorius, did a master's on this, to develop a relationship between the riding quality of the road, how rough the road is, and the shelf life of the tomatoes. Because when we spoke to the tomato farmers, they said, listen, the best way to identify the condition of a tomato is to understand that a good tomato has got a 10-day shelf life. And if we can get to a 10-day shelf life, life is good. But tomatoes that's not in a good condition may go off after 6 days or 5 days or 3 days. And that is what affects our income. Because if the consumer comes and buy our tomatoes today, and after 3 days they are not good anymore, they don't come and buy our tomatoes anymore. Or they pay less next time. So if we can have a 10-day shelf life, people will come back, they will buy our tomatoes, they will use them. So what she developed was this set of relationships. It's there for red, pink, and green tomatoes. Now, red, green, and pink is not just, that's a color. They've got nice detailed color charts that actually, I think they've got 7 to 9 actual colors that you define the ripeness of a tomato with. So that will be a ripe tomato, that will be an in-between one, and this will be, as it says, a green tomato that's not ripe as yet. And the reason why that is important, and if you don't believe me, go to the supermarket tonight and first pay for the tomatoes, don't just try them there. But get a green one and a more red one, and just feel what they feel like. A green tomato has got a higher stiffness than a red tomato because it starts to deteriorate as it gets ripe. So we've done it for the different ripeness of tomatoes, but we also have done it for the different levels of how many tomatoes you've got in a certain container. Because sometimes you buy a container that's only got 1 or 2 layers of tomatoes, sometimes the middle one, and sometimes in bulk you transport it in the bigger containers. So that allowed us to have these relationships where we can say, if you transport tomatoes for a certain duration of time, the different lines is 6,660 seconds as an indication of it's a short trip or a short section of your road that's in a bad condition, or it's a long section of your road that's in a bad condition. You transport them on a road of a certain roughness, the outcome will be that the shelf life is still 10 days, that's fine. Which means from a riding quality viewpoint, I did not affect the condition of the tomatoes, or as life changes, it starts to deteriorate as the roughness gets worse. So now we were in the position to get back to the roads department and say, guys, this section of road that's got a riding quality of 10 meters per kilometer is causing us so much loss in income when we transport our tomatoes on this road. Can you please fix the road? The reason why it becomes important for the Department of Transport is I'm the farmer. So I produce very good tomatoes. I put these very good tomatoes on my truck and I travel on the road that you have to maintain to the market. If you maintain the road very well, it means that they arrive in a good condition. People pay me a lot of money. I make a lot of profit. I pay a lot of tax. And the tax goes back into state coffers to maintain roads as one of the things that the state has to do. But if the road deteriorates, it means that my very good tomatoes don't get in a good condition at the market, which means that my income drops, which means that I can employ less people, which means that I've got a smaller profit on which I pay tax, which affects the income to government to look after roads. And once we started to discuss this model with the local roads agency and the provincial government, it suddenly became very clear to them that it's actually in their benefit to improve the condition of the road. It's not only the farmers that's going to get the benefit out of that, but the community will benefit because of the higher input or higher income, but the state finances will also benefit, which allows them to do more improvements onto the roads. So this was quite a major step forward. Then the next step was we got back to the States. And we said that sort of as an intermediate step, it's good to have measurements on short sections, but what happens now if you transport stuff over a long distance? Because now a lot of things are out of your control. So we, in this case, did not work with tomatoes, we worked with berries. We installed sensors on a truck. There you can see a number of them measuring the acceleration on the body of the vehicle, measuring the acceleration on the axle where you've got no suspension as yet, and measuring the acceleration on the boxes of berries. And then we took that truck and it started in Watsonville and it traveled all over the country to Dover in Florida, transporting these berries. And there's a lot of additional data, but just as one example,
Each of the lines is pretty much where it went from one state to another state. And what you see over here in these lines are the yellow line is the body of the vehicle, and it's a ratio between the acceleration of the body of the vehicle and the back axle as an indication of how much acceleration, how much bumpiness we get in the system. So you can see the body is not too bad, but there on the boxes of berries, middle of the berries and top of the berries, you start to get, especially in some areas, quite a lot of acceleration, so quite a lot of shaking of those berries as you transport them. The reason why this is important, this led to the current study that we are busy with in South Africa that I'll show you in a few slides, of not only focusing on one small part of the solution. And as engineers, it's important that you understand that whatever you focus on is almost always part of a bigger story. And you can optimize that small part of what you are working on 100%. If there's a bad link somewhere else in this chain, things will still be bad. So if you look over here, if you improve that section of the road that you've got no accelerations, that it's absolutely smooth, but this part of the road is still bad and you don't know about it, then your berries will still get to this point in a bad condition. So you need to sort out your part of responsibility, but then also stand back and say, but how does this fit into the bigger picture? So in terms of taking this model further, when we had a discussion with the local guys in South Africa, a lot of the avocado pears in South Africa are exported to Europe. And they started to say, well, okay, we've got an understanding of what you do on our roads now, and we've got this discussion about tomato transport and avocado transport, but we transport stuff from the farm to Europe, which means we have to harvest the avocados in this case, and we have to clean them, we have to pack them. There's a local transportation network, then there's a transcontinental sea part, and then a portion up there in Europe where we don't have any control about. So there's parts there that we can improve the condition of the road, but there's parts that we don't have a clue of what's happening to this avocados that we are exporting. Can we measure the effect of each of these parts? So that's a current study where we then started and say, okay, technology changes. We need something better because we cannot put in these mats for that whole trip. So I've got another student, and for his master's degree, he developed, well, I'll show you a few slides towards the end, an intelligent railway ballast, which is basically railway ballast, the big aggregate that you use in rail. That's wireless and everything that you use to measure what happens to that ballast as the train goes over. So we used exactly the same technology, which is the inside of that. We 3D printed avocados, and they are wirelessly charged as they sit over there. So we've got 3D printed avocados. That's a harder type of plastic because the condition in which avocados are normally transported is very hard. But we've also got a flexible one, which is the tomato one, because the tomato is obviously softer than avocado. But the inside of all of that is a little computer with GPS and accelerometers and gyroscopes and temperature and light levels, which means that technology-wise in 2012, this was not possible at all. Now we sit with something that's that big, and I can collect all of this data for the whole trip. So once we had that, we said, okay, you have to start in the field. And you will see this guy that harvested it. This is how they harvest the avocados. He's getting to the containers over there. That's the smart avocado. This is important because it doesn't help me to sort out the road. And the way that they harvest it and pack it and throw it out and stuff cause a lot of problems. So we started to measure at the tree. Then that's the portion where they drive in the field itself. That vehicle that they use doesn't have any suspension. And that's not really a road. It's a gravel farm section of road that they drive on. So you can see a lot of bumpiness in that portion. And then after all of that, they get to the pack house and they dump it out. And the MOC is going on that whole cycle of moving through the pack house. So fortunately, the client that we've got in this case said, listen guys, we know you are civil engineers and pavement engineers and you are interested in the pavement part of this, but we realize that that portion and that portion is as important in this chain of events. Because if we perfect the road over there, but the avocados bumps up and down in this part of the system, they are still going to get damaged. So although we are busy with the big project now, we are, as part of that, doing 52 pack houses, where we just measure the effect on these avocados from the moment that they are dropped in the pack house until they are in the box. Because they want to also look at what's the worst conditions that they measure over there. So if you look at, this is just the accelerations, for instance, for this trip, that first portion that you see over there is in the field. So that's where the guy gets it out of the tree, throws it in a bag, walks with the bag, dumps it in another container. Then it waits a while. Then it's that first tractor part where it bumps up and down, no suspension, transportation. They stop, load it onto a truck. This is just a waiting time until everybody loaded up. This is a part that we traditionally had a look at. That's a paved section of road, that's an unpaved section of road. And that's what happens in the pack house. So if you do not look at the big picture, you only focus on that portion and you say, wow, that's bad. We have to sort out the effects of that gravel road and get this in a much better condition. But you don't see that and you don't see that. So it's important to stand back and understand, I'm focusing on this, I'm the specialist on this, but how do we solve the big picture in terms of our transportation? So that's just, if you look at the acceleration, the harvesting, the bad part in the field, the paved road, gravel road, and the packaging. But then it's not only acceleration, because what happens to these avocados as you transport them, they also roll around. That's where you have to speak to your client, because your client, the avo farmer, tells you, but as avocados roll around, they start to damage the skin. And this is not good for them. So the first one shows us the accelerations. The second one shows us how much roll happens. And again, you see on the road itself very little. In the pack house, a major lot, because that's happening the whole time. So you have to look at what happens to the skin over there. And then, as engineers, we want some way of expressing this. So we calculate this as a cumulative kinematic energy. How much energy is going into that avocado as you transport it? Because obviously, the higher the applied energy, the higher the potential damage to this specific avocado. And it all started because we are interested in the riding quality and how the riding quality affects the users. So I've got another student, and she said, okay, this is fine. You guys are interested in maintenance of roads, gravel roads, because that's actually how we assist this avocado and tomato farmer. But we all know we want to improve the condition of the roads, but by how much must we improve the condition? Because the whole road network over here is unpaved roads. They drive up and down in the mountain to go and harvest the avocados, down there to the pack house. But how often should they maintain this gravel road, and by how much? So she did another project where we took images, we've got cameras on their vehicles, images of the road condition. We collected data over a year or two on the average riding quality on the road, on when it rained, on what happened after we maintained and graded the roads and so on. And then she combined all of them, and unfortunately I don't have the final graphical part of what she's done. But then she combined the 3 lines over there, which are the shelf life equations that you saw earlier, together with the annual hourly cost for grading the road. Because obviously I can come and grade the road every day and it will be in a perfect condition. It's going to cost me a lot of money. Or I grade it once a year. I save a lot of money, but the road is in a very bad condition and my shelf life gets affected. So what she's done by doing all of that, started to realize in terms of maintenance of the roads, if you've got sections of the road where the slopes are more than 6% and it's a mountainous area where the avocados are growing, obviously you need more maintenance. The sections with less traffic and flatter, less maintenance. And those are sort of the obvious things. But what she done in the optimization then is to get to this point. This is again where it's important to understand people are using your road, you need to understand their needs before you tell them how often you need to maintain the road. If you've got high market demand for tomatoes, then a long shelf life is not really needed, because a lot of people come and buy your tomatoes, they consume the tomatoes within 3 or 4 days, and they come and buy new tomatoes. So they don't care whether the shelf life is 10 days or 9 days or 8 days. As long as it's more than 3 days, they are happy because they consume good tomatoes. So if you've got high market demand and low shelf life, then it's actually okay to harvest tomatoes that's more ripe and to maintain the road. Value of 4.6 meters per kilometer riding quality is a worse condition than 4. So you don't have to maintain that road at a higher cost to the same level of quality, because the user will be quite happy with what they get. And this saves the farmer money, because they don't have to grade the road every week, they can grade it every 2 weeks. On the other hand, if you've got low market demand, people buy the tomatoes and they leave it on the shelf for up to 10 days, you better make sure that it's still in good condition after 10 days. So in a low market demand situation, you have to make sure that your roads are in a good condition, because the effect of the roads on the tomato condition is going to show earlier to the consumer, and that will drop your income. Looking at all of that, putting it together from a road maintenance viewpoint, we also then developed a model for them where they are in a, let's call it a semi-autonomous road maintenance procedure, because the trucks that they use to transport these tomatoes has got sensors on that's got various telematics in, and they are calibrated to continuously provide us with the riding quality of the road. So as the truck drives and it's finished, you get a little indication that that's the condition of that road. Those are the bad spots on the road. So the vehicles actually tells us where are the bad spots on the road. We don't have to have a dedicated measurement device that you send out once a month or once a year. Because we immediately know the condition of the road, we get a picture like that. That's that section of road that tells us that's the required riding quality. All of the spots where the riding quality has got a higher number is bad. Go and fix those specific spots with the grader and leave the rest alone. By doing this, these guys save between 40 and 60% on their blading or maintenance costs, because suddenly they did not have to go and blade the whole road. They focused on those sections. In terms of the semi-autonomous road maintenance, what happens now is the truck drives on the road. The truck reports automatically through the telematics that this section of road is bad. That message gets to the grader operator, and we are not totally at the autonomous grader as yet, but he gets a message and basically tells the grader operator, go out to that section of road and go and grade it. That's the job. It's GPS linked. It tells the system, I've graded 2.5 kilometers of this road on that section, so they can lock the fact that the work has been done. And the next truck that drives on that section of road reports back and say, listen, the riding quality is now at this level again, so it's fine. So we drop the effect of the riding quality and we improve the road condition. So all of this is important to understand, that you need to understand who your ultimate client is. Whether it's a tomato farmer, or somebody going to school, or somebody traveling somewhere, or transporting whatever, because all of that knowledge affects the way that you do your job in a better way. As I said, the electronics that allowed us to do it started off with those little computers. Those are the smart ballasts that we started to develop. It links a lot of technologies that starts to become easier and easier to do. And by doing that, this is an example of the ballast, for instance. Again, something that without the type of technology would have been very difficult to measure. As the train goes over this position at different levels, we start to measure the actual movement of those ballasts. And now you can say, well, but that's sort of almost robotics and things like that. You are a civil engineer, why are you interested in this? Because the moment I know how much movement there are in those ballasts, I can talk to my engineering geology colleagues and say, if I've got this type of aggregate and there's this much movement between them, how quickly is this type of rock going to deteriorate and affect the quality of my rail network. So it's knowledge that if I don't have that, the engineering geologist will tell me, okay, that rock is better than that one, but I can't tell you by how much. So you start to quantify your damage. The same way, we developed what we call snoot. Now, snoot, for everybody that's not Afrikaans, that's my home language, is actually the word that you use for the nose of a pig. So, and snout would be the English. So, snoot is a little device that we then put together. It's wonderful to be at the university and have a very good student. Because we actually started, I'll show you, this is the location of our new laboratories in Pretoria. Got a major highway over there and over there. That's the experimental farm. We were interested in the environmental conditions or the air quality next to the building as we've got congestion on the highway. So the student that's done the clipping, which is the smart ballast, we had a discussion. I said, listen, I want to measure this. And he said, yeah, I think it's possible. And I said, okay, let's make it easy. What can you measure? And he said, okay, no, you have to tell me what you want to measure. I said, no. Tell me what you can measure, everything. And he literally went through the catalog and said, I can measure light and acceleration and gyroscope, pressure, any volatile compounds, CO2, light, infrared, UV spectrometer, particulate media. And we said, okay, let's put everything that we can measure into this sensor. This is our base sensor. Because on that whole farm area, we've got a lot of agricultural activities. We've got other clients that's interested in what's the environmental conditions. Again, looking at the way the technology changes. 2 years ago, you couldn't do that. This is one of those projects where halfway through building this, we realized there's new sensors that came out, so we can start to incorporate them. And currently, we are working on a system where we will have that grid over there. With the growth of technology, we can also attach snoot to our drone and say, but you don't have one level of environmental condition. As the traffic drives over there, there's probably some changes in the air quality as you go up and down and the way that the wind blows. This is some of the initial data that we have. As just a sort of a quick 10-hour shot. The yellow is change in humidity. The gray one is as the temperature changes, but the CO2 is the blue one. And the total volatile organic compounds is the orange one. This is where congestion started to happen. So again, there's technology that develops that starts to provide you with inputs into your models that you can really measure data. You don't have to just use a model that tells you based on some calibrated model, this is what they expect for this amount of traffic, the CO2 levels to be. You can go and measure it. It's a little box that big and you collect the data. So it's important to keep up to speed in terms of technological developments, because what you guys know today, in a year's time, there will be better stuff, improving your modeling, your characterization, your quantification of data. And the better your data becomes, the better the answers can be that you are looking at. So to finish off, because this is, according to my colleagues, this is like my grandson. And you will know, if you're a grandparent, you've got a little book of photos you show to everybody. I've got them on my phone. That's the way that they work. But this is actually, we started 6 years ago, and our National Roads Agency said, we've got a need for a reference laboratory. We need a place where we can bring materials from all of our roads in South Africa, where we do third-party independent reference testing of the properties of that material. But while we are doing it, we've got this open area on the campus. Can you also add a training laboratory? And while you do it, can we expand your concrete laboratory? So all of that was put together. And we've got a training laboratory. And the reason why I'm telling you this is not only to brag about the very nice, beautiful new laboratory, but you have to understand where your data originates from. You guys are clever master's PhD students. You do lots of calculations with lots of data. of long equations. But where does your data come from? If you are working in pavements like I do, there's a technician that does most of your testing. And that technician is the source of your data. I'm not talking while you're studying, sorry, then you don't do your own testing. But the moment you start to work, if you go to Caltrans, they've got a laboratory where technicians does the testing. That technician doesn't do their job well. You, as the clever analyst, get data that are wrong. And you make major decisions based on the wrong laboratory data. So that's the main reason for this training laboratory, to make sure that we train our laboratory technicians to the same level and quality as we train our engineers, that they understand you have to provide the engineer with a good data set. But as part of this, again, linking technology to it, we realized that in terms of training manpower in South Africa, we've got a lot of people that would like to become a laboratory technician, but they are far away from a laboratory. So it's expensive and difficult to get to a laboratory to get trained. So our colleagues in the IT department developed with a standalone headset. Again, technology changes. 2 years ago, you could not do it like this. You had to have a big computer to set up the whole system. Now you've got the headset and the two handles, nothing else required. We've got, this is a sieve analysis test on the virtual reality system. So although it's like a video over here, you can see the guy doing the test over there. You can send this little box, which costs about less than $1,000, let's say $800. You can send that box to a guy in some remote area where he's got no access to a laboratory, and say, put it on your head and start to follow the instructions. And do this test until you've got the muscle memory to understand what you're doing. And once you've got that, you can come to my laboratory and we do the final training of how to do it. And that person would have seen the laboratory, would understand the test, and the VR is such that we are engineers, and engineers never grow up. So what we did when we started to get this is the nice version of the video. I can tell you, if you take that bucket and you sort of lose it, it falls. If you take the bucket full of soil, you saw the soil over there, and you turn it around, the soil falls out. So it's reality. It's not just sort of there's a video and whatever you do don't matter. You have to be careful. Otherwise, stuff falls off the table, the soil falls out, it doesn't work anymore. So it's a major part of the training. It's good fun on the one hand because it's VR and all of those things. But for a guy somewhere in the rural area, this is his career. He or she can learn from this how to do something, come to the laboratory, be trained, and it becomes part of their socio-economical development. So it's a nice, cool part of our laboratory. We're also busy with the reference laboratory. For the reference laboratory, what's important is to do a comparison between what the laboratory test, the field test on a contract is doing, and our third-party version of the testing to make sure that the data are correct. But now you can do it between those two laboratories and get some results, but the more important part is that it's also supporting the proficiency testing scheme. Now, a proficiency testing scheme basically says the following. Within South Africa, that's where we are located. This laboratory, this reference laboratory, will prepare standard samples of materials, do the tests ourselves, and send those samples out to various laboratories in the country. So you also do the test, and then we compare the results and make sure that the various laboratories actually get similar results for certain tests. But apart from within the country, also allows us in the Southern Africa area, where there's lots less reference laboratories available to do that comparative testing, and also with the various international proficiency schemes to make sure that the testing that we do are up to standard wherever we want to compare that. So the laboratory itself, a major role to play in that regard. And then lastly, in terms of the layout and what we've got, that's the sort of the phase one development that we are busy with. So we've got the training and the reference lab where we obtain material properties. So we test one asphalt, one bitumen, one granular material on its own, and we obtain the properties. But we know that the road pavement is not one material on its own. So apart from that, we've got an accelerated pavement testing site also on the whole area where similar to what you've got outside here at the PRC, you can test a combination of materials. You've got a surfacing and a base and a subbase and a subgrade. So if you put all of those materials together, you can see what's the expected performance of this pavement structure. And where we are really fortunate is that right next to the laboratory, that's a fence of the laboratory, we've got a highway. And because the National Roads Agency is the sponsor of the project, they said, we asked, but it's like when you ask for a Christmas present, you think, I'm going to stretch this, I'm never going to get a bicycle. You ask for the bicycle and your parents come and give you a motorbike. This is pretty much what happened. We told the National Roads Agency, you know, there's 1 or 2 laboratories in the world where they've got access to a real road. Wouldn't it be cool to have a section of the highway? They said, yeah, but just not there, that's on the curve. Let's just move it there, it would be longer. So they actually constructed a lane specifically for the laboratory where we can install sensors inside the pavement, next to the pavement, over the pavement, however you want to do it. And then we open it for the real traffic, get real traffic on the road, got the students on that side of the fence, they can see exactly what's happening. Can take the traffic off to the old section and say, guys, come and see what the pavement looks like where you had traffic. So in terms of going from materials to structure to real pavement with real traffic, provides us with that full circle of information. So John, sort of I-80, I think is close enough to you guys. Easy to edit.
We'll take 113 if we can get it.
No, yeah, I mean, that's closer and easier, so we'll send you the plans. So the benefit of all of that is that we've got this real, this is why I say it's like my grandchild. We've got this real state-of-the-art, that's reception, training lab, reference lab, concrete lab over there. And this is the real traffic section that we've got where you can put all of this research together. All of the stuff of test a tomato over there to see how much damage. Then you come to the real road and see but what's the riding quality on the real road and how that is affected into the bigger picture. And to put all of that together, to construct and maintain and manage a road for the benefit of the user. I think if that's the one thing that you remember from the talk, I would be quite happy. You are not doing your job because stresses and strains are important. You are not doing it because your model parameters in a transportation model is important. Those things are only important if they support a better road. One of the old pavement professors, Andre Molenaar at TU Delft, one year at the conference, where we were young, a lot of people presenting a lot of good papers. When we had all the discussion, he summarized and he said, listen, you have to remember, when I get home at night and I greet my wife and she says, how was your day? And I start to tell her it was such a good day. I've done these calculations and these measurements and stuff, and the stress is smaller than that one and stuff. She tells me, listen, stop. If what you've done today is not going to make the road safer, and cut down on the congestion, then I'm not interested, because then you haven't worked. And he was slightly annoyed by the answer initially, because he's doing real cool analysis and stuff. He said when he started to think about it, he realized, yeah, she's right. Because you're not an engineer or a transport planner or so on, because that's important. You are doing that job because people need to use that facility. People need to be able to drive from here to San Francisco without too much congestion. Let's say it like that, because you will have limitations in terms of budget and availability, but you want to provide them with a safe drive, least congestion, no problem with possible accidents and so on. And your job is to, within an optimized, limited budget, do that job and provide that service to humanity. Then you are doing your job. Not when you get, this is the detailed stress and strain and parameter analysis for this transportation model. So that's about it. Any questions?
Before there's a question, just a heads up. I don't think this is a secret that the university is actually ITS, which we're all associated with that, is actually trying to see if we can set up a similar facility somewhere near Davis where we connect a real world facility with a closed circuit facility with the laboratories that go with it. The model for this is in Aachen, Germany. And there's another one in Virginia, the Smart Road in Virginia, which they also close loop for the automated vehicles and how all of these different types of vehicles operate on these roads as well. Always fun. Any questions?
And this is maybe a little off topic, but in the analysis that included the harvesting and packaging of the tomatoes and avocados, were any changes made to the other parts of the processing as a result of
They are actually currently looking at the packaging warehouse. There are aspects of that they started to highlight and say, listen, but the way that we dump the avocados over here, we can now see that's actually a bad way of doing it. We did not have the data before, so they are smoothing some of those processes. They are also looking at limiting the speeds on some of the roads where they cannot fix the road, because the moment you start to drop the speed, less of an effect on it. And as a very real example, the ZZ2 guys got into a partnership with the local government, or the provincial government, where there were sections on the road that was really bad. And provincial government said, guys, we don't have manpower to fix this now, can you help us? And they actually got, in South Africa, you can still do that type of thing, public-private partnership type of thing, and said, okay, if you guys can fix this section of road, we will sign off on it, and you save on taxes in some way in the end. So there were actually good examples where the data that they obtained allowed them to change some of the processes and make them run a bit smoother.
One of the questions we've had, and we didn't quite get Caltrans to bite on it this time, is anything that you're aware of, the vehicle maintenance and cost issues, and we're very curious about the interaction of the pavement vehicle interaction and the life of a battery, a vehicle battery electric vehicles. Because if you're shortening the battery life through the vibrations, that really changes the environmental impact and the cost of those vehicles. We did learn that fuel cells, hydrogen, likes to get shaken a little bit because it makes the molecules work a little better. But anything you're aware of in terms of alternative fuel vehicles?
We did not investigate that at all, because currently the South African model, these guys use normal diesel-powered vehicles and so on. They did tell us in terms of their normal lead-acid batteries that they did some changes there to make sure that they are more stable in the system. But it was not really advanced type of work. It was just, listen, we can see if the road is bad and stuff just shakes, you start to loosen connections, and that starts to affect it. But I think it's a very important part of it. And again, the link to the whole environmental benefit of it, because you normally don't even think about it. It's okay, the batteries will not last so long, it's going to cost me a lot of money and so on. But what you have to realize is the fact that if you decrease the life of the battery in that electrical vehicle, it means you need more natural resources to build another battery in a shorter time. It's the same with the tires. If your tire wear is higher on a certain type of road pavement, it means that you will need more tires over the life of transporting certain stuff. Because what you need to keep in mind always is there's so many people that, let's keep to the example, that wants to eat so many tomatoes. So if you use one set of tires transporting from there to there and you have to replace them, or you improve the road condition that you can use one set of tires for 2 trips, that's a major environmental benefit, because you save on the natural rubber and the emissions of manufacturing those and discarding the tires. So we have not looked specifically at that, but I think there will be a real good example of how that cost also goes up, because most mechanical stuff don't like shaking. Sort of vibrations is typically bad in the long term.
Actually, to follow up on that, my understanding is that in a lot of the developing world, like Ecuador, some other places, tire replacement is one of their greatest sources of carbon emissions, and the use of tires is one of their greatest sources of carbon emissions.
And unfortunately, most of those guys also don't use the discarded tires for anything beneficial. We use most of that rubber back in rubber surfacings. So putting it back in the road, it's got many benefits. The problem is still if you use too many tires, I mean, it's too many natural resources that you use. So you want to stop that. Yes.
In terms of like creating the optimal road routes where VOC is decreased and things like that, how would you implement that and then ensure that people are actually driving those routes? Because especially like some people might prioritize time where they might not have like the money to invest in like spending more time and like gas on those roads.
The important part there is to make sure that people understand the benefit of the lower vehicle operating costs. It's like, how do I convince you, and I'm not sure whether this is correct or not, if it's costing you $50 to travel with your vehicle to San Francisco, and it's costing you $40 to use the train, how do I convince you to do that? And I specifically give the example like that because the $40 on the train is not necessarily better than the $50 on the road. Because there's various other things that comes into the equation. The train may take me 2 hours and a half, but at the wrong time of the day, the road may take me 3 hours to get there. And suddenly, the answer is different at peak time than it's off-peak time. So you have to convince people by providing them with the full understanding that they realize, okay, there's not one single answer. Optimizing that is not one answer to always take the train. Because always take the train, if I'm 4 people traveling, it's 4 times the train ticket, and now it's much more expensive than using the car. And in the same way, by working with the farmers in this case, and having them understand that if they drive that route, which is 5 miles longer than this one, they actually save money because on that road they don't have to stop and the condition of the tomatoes at the end is better. That's how you convince people. You don't convince them by telling them you shop, because we are people, we say no.
So actually, although Yolo County, our #2 crop, is processing tomatoes, another example which we'd like to get to, and again, we haven't quite been successful on getting the funding for this, but if anybody's interested in this, I'll throw out, UCPRC is interested in putting together, we've been talking to Wynand about this, we partner with Wynand. We're looking to be able to produce, right now, what are the 2 choices that you get when you pull up a maps? What are the two pieces of information you get to help you select your route? Google Maps, Apple Maps, what are the 2 pieces of information they give you to select your route?
Time and distance.
Time and distance. With the models like this, what we want to get to is a smartphone app or a logistics app for the trucker that will say, wouldn't it be great if you could pull up CO2 emissions, which we can do with these models, integrating these models. And that's a third piece of information that you get is what are my carbon emissions, walking, train, and taking this route versus that route, because the emissions for a given route in a vehicle, in an internal combustion engine, are going to be a function of your speed, which we have the models for, your vertical gradient, which we have the models for, and your roughness, which we have the models for. So we'd love to be able, we haven't gotten anybody to bite on this yet as a proposal, but if anybody's interested, we're looking to tie these models together into an app that gives you CO2 information. And then for truckers, we want to tie this into an app that can give them this type of information so that they can figure out for a given product, their lowest cost route, considering all this information. We're pretty sure one of our former graduates, Wei Shen, works for Walmart, and we're pretty sure she's doing this for Walmart, but we would like to, I'm not sure because she can't tell me. Similarly, our student working for Apple can't tell us some of the stuff that he's doing for Apple, but that's the kind of app that we'd like to get to. Now, where is that data coming from? farmers in South Africa, but also SANRAL, the South African National Roads Limited. But Caltrans has this data. We haven't been able to quite find the right person at Caltrans yet to be able to put this app together, and then there's litigation issues and so on. But that's the world, that's the vision we're trying to get to, which is support better decision-making for different criteria. And that's really the bigger picture. In South Africa, the big issue, went down to talk about carbon emissions in South Africa, and they said, yeah, tell me about jobs created, tell me about improved access to healthcare, then talk to me about carbon emissions.
And I think that example is again getting back to supporting the road user or the bigger user and optimizing your answer. Because optimizing the answer is never one answer. In a certain economy and environment, it is lowest emissions. In another economy, it's forget about the emissions, how can I get more jobs? Another one it is, how can I get my goods to the market the quickest way? And you have to understand that part because before you can solve the problem of the user. Otherwise, no use. If I come to the US now and I say, guys, I've got this totally new way of planning your transportation and you are going to create so many more jobs. It's sort of, oh, well, unemployment's not that big an issue. I mean, we sit with, depending on who you listen to, between 27 and 47% unemployment. You guys don't have a problem with unemployment. So if I can change jobs, major issue. If there's a bit of emissions coming out of it, oh, we know it's bad, but guys, 5 more people can eat. So you need to understand why people need to move, why they need to get transported before you can answer their question. Otherwise, you only answer a small part of the question.
All right. Any last question? All right. Thank you, Wynand.
Pleasure.